Good afternoon, everyone, and welcome to today's sponsored ABC webinar, Sorbent Tubes in the Measurement of Metals in Gaseous Fuels. My name is Caroline Pete, and I'll be facilitating this webinar. I want to give a big thank you to Ohio Lumex for sponsoring today's webinar. Their sponsorship directly supports the ABC and our program, so thank you very much. Before we get started, I just want to go over a little bit of housekeeping. First of all, you should already be able to hear me, and you should see a slide titled Quick Notes. If you're hearing echoes or your sound quality is bad, you can change your audio function in the audio tab on the GoToWebinar toolbar, which is probably on the right side of your screen. If you're still having any trouble, you can send the organizers a message here using that questions tab that you see on the right side of your screen. And don't worry, we are recording the webinar. The recording and the slides will be sent to you by Friday. If you have any questions for our speakers today, you can ask those in the questions tab as well. We'll be handling questions at the end of the presentation. Ohio Lumex has also provided handouts for you. You should see 3 handouts in the handouts tab. We'll also include those in our post-event email as well. And so with that, I'd like to thank you all for joining us today, and I'm going to hand it off to our moderator, Patrick Surface, to take it away. Patrick, it's all yours.
Awesome, thanks, Caroline, and thanks again to the team at Ohio Lumex. They're the leaders in gas analysis and have their facility in Ohio, as you might not be surprised to hear. And this is going to be a really great opportunity to dive into just one part of what they do. You know, when you're looking at your gas specs and trying to make sure that your RNG complies with your utilities gas spec, there's at least in our recommended spec that ABC has, there can be a lot of detail, and sometimes there's not a lot of detail on what to do about metals. And when you look at the test that is the method that's used to determine how much metals you might have in your gas and to be able to meet that spec, at least, you know, my understanding is that what Ohio Lumex is offering here, and in conjunction with the EPA, is going to be probably cheaper and a lot safer than the most common practice, EPA method 29, for doing this analysis. And so, I don't know, if I were in your shoes and needed to do some analysis, I would definitely love to be able to handle fewer toxic materials and save some money too. So I hope you'll be as interested as I am to get into what they have to share here. Jonathan Cross from the Ohio Lumex team is going to be leading us off here. Bennett Rubin's in the background here and may jump in for any questions depending upon which direction we go. But at this point, I'm going to hand it off to Jonathan. Put your questions in the questions tab as they come along, and we will handle those at the end. So Jonathan, it's all yours.
Okay, yeah, thank you for that introduction, and thank you everyone for attending this webinar. I hope you find it interesting. So as Patrick said, my name is Jonathan Cross. I'm the Director of Technical Services here at Ohio Lumex. Many of you may already know about us, but for those of you who don't, we build monitoring equipment to monitor various gas constituents in gaseous fuels and other gas matrices. We also operate a laboratory that analyzes trace pollutants and contaminants in ambient air, source emissions, renewable natural gas, and biogas. We sort of specialize in measuring things that are typically very difficult to measure. And over the last couple of decades, we have spent a lot of time and effort working to improve measurement technologies for a wide range of applications. And what I want to talk to you about today is the most recent improvement that we've made, which is the measurement of trace metals in gaseous fuels. So that would be biogas, renewable natural gas, or fossil gas. But before we get into the details of the development, I first need to provide a little bit of context and background so everything is clear. So first of all, this webinar obviously is about a new measurement method for metals, but why are we measuring metals in the first place? Well, utility tariffs and gas quality specifications across the country often include limits for specific metals that are considered either carcinogenic or non-carcinogenic health protective constituents. If these metals are present in the gas at significant concentrations, they may pose an exposure risk to consumers. Essentially, renewable natural gas producers that want to sell gas to a utility must first demonstrate that their gas contains certain metals below specified concentrations. And right now, these metals include copper, arsenic, antimony, and lead, but other metals may be added to various utility tariffs in the near future. We know at a minimum, chromium and cadmium will be added to some tariffs, and I wouldn't be surprised if other metals are added in the future. The next question is, what are we trying to accomplish by developing this method? The bottom line is we want to replace a method called EPA Method 29 with sorbent tubes. And I'll explain what EPA Method 29 and the sorbent tubes are in the next couple of slides. Next. So this is a typical sampling system for EPA Method 29. This method is designed to be used in stacks to measure metals being emitted into the atmosphere at stationary sources like coal power plants or waste incinerators. It's a fairly complex sampling system that includes isokinetic sampling nozzles, a glass probe liner, a heated quartz filter, and impingers with hydrogen peroxide and nitric acid. Stack testers understand how complicated this method is and acknowledge how easy it is to accidentally contaminate the sample train with metals from ambient air around the sampling location, since all it takes is a single piece of dust to bias the results. Next. That complicated sampling system was simplified to be used for sampling metals in gaseous fuels like biogas or RNG. The isokinetic nozzle, probe, and filter were all removed, leaving nothing but the impingers in what's called the back half of the sample train. The reason for this is twofold. One, it's not possible to sample isokinetically in a gas pipe simply because we're, not working with a 4-inch diameter sample port where we can fit a large probe. And two, the metals in gaseous fuels are almost entirely in the vapor phase, meaning they're either methylated metals or metal hydrides. Now, I'll put an asterisk on that since that is what we've observed so far through our own field data, and that's what we've seen published in literature, but we are working with others in the industry to determine whether that's universally true. It's possible that there could be some metals contained in particulate matter, but again, from what we've seen, basically over 99% of the metals in the gas are actually in the gas phase and not bound to particulate matter. In any case, back to method 29, the principle behind the sampling method is that the sample gas is pulled through a series of 3 impingers. These impingers are essentially like cylinders that have a solution in them. It's like a bubbler. The first 2 impingers contain a mixture of nitric acid and hydrogen peroxide, which absorbs metals. The third impinger is an empty chamber that helps to ensure acid and water mist do not escape the sample train and get into the metering system. The metering system can vary in design. What I've illustrated here is our sampling system, which uses dry gas meters to determine the gas volume that passes through the sample train. Now, this method may work just fine as long as the absorbing solutions are effective at capturing all of the metals. However, there are several complications. The nitric acid and hydrogen peroxide have to be mixed in the field immediately before sampling because the solution is not stable over long periods of time. The chemicals are hazardous, meaning you have to use hazmat shipping when shipping the reagents on site and when returning the samples to the lab. These chemicals also pose a risk to the sampling engineer. Additionally, there's a high risk of sample contamination from ambient dust while handling the reagents, impingers, and sample containers in the field. The concentration of the absorbing solution actually goes down over the course of sampling because it's diluted by water that condenses inside the impingers. This causes the absorption efficiency to decrease over the course of the sample run. And finally, you end up with approximately 250 milliliters of sample solution when running method 29 in this way, which is significantly more than what you have after processing a sorbent tube. So unless a laboratory cooks the solution down to a smaller volume, this means method 29 will yield poorer sensitivity than the sorbent tube because the solution is more dilute. Essentially, what I'm saying is for a given gas volume, let's say 30 liters, you're going to have a certain mass of each metal that is captured in the sample train. If that mass is diluted in 250 milliliters, you have a lower concentration in that liquid solution than you would when running a sorbent tube, which uses a smaller volume. Next. This is an illustration of a sorbent tube sampling setup, and there's a picture of the actual sorbent tube there on the bottom left. The tube contains two sections of sorbent material separated by a specially designed inert foam plug. Sample gas is pulled through the tube, and the metals are captured in the first section, which we call the primary section. The second section is called the breakthrough section and is used to determine whether a significant fraction of the metals in the gas stream passed all the way through the first section. Ideally, the metals measured in the breakthrough section are 0 or extremely low relative to the primary section. The sorbent tube approach offers several advantages over method 29. It's easier to ship, it's safer, it's more difficult to contaminate, it is more affordable, and by default, you get breakthrough measurements when using a sorbent tube. Additionally, since each sorbent section ends up being processed into a 50 milliliter solution, the samples end up being more concentrated. Again, this is what I was referring to on the last slide. This means that you can measure lower concentrations in the gas, assuming the method 29 solutions are not cooked down to a smaller volume in the lab. For these reasons, we pursued the development of the sorbent tube to provide a superior alternative to method 29. Next. So that's some background on method 29 and the sorbent tube method. Before we go through the rest of the presentation, I want to provide some more background behind the research project so you all understand where this is coming from. The work we did on this project and the data I'll show was not all specifically oriented around gaseous fuels. In fact, the project was primarily geared towards emissions applications, and the gaseous fuels work was done in parallel. So in late 2021, EPA released a solicitation for proposals under their SBIR, or Small Business Innovation and Research Program. And in that solicitation, they included a research topic aimed to develop a method for the continuous measurement of metal hazardous air pollutants from stationary sources, which would include waste incinerators, metal scrap recycling plants, smelting plants, and several other categories. So in addition to those sources of pollution, we identified coal-fired power plants and cement plants as potential applications where this technology could be used. We also recognized that if we were successful in this development, we could transfer and adapt the technology to the gaseous fuels space. Until we developed this trap, the only method for measuring metals in gaseous fuels was the modified EPA method 29 I just described. So in response to that solicitation, we wrote a proposal and submitted it to the EPA. Shortly afterwards, we were awarded a contract and began research. Next. Now we're going to get into some of the details of the development process. The first problem we needed to solve was the problem of background metals in the tube. So as I said earlier, it's it's critical that our breakthrough be as low as possible, but a challenge there can be, if you have a lot of background metals, it can be difficult to distinguish between what is the background and what is the amount of metal that you've captured from the sample gas. So it's very important that the sorbent tube material itself be as clean as possible, or in other words, have an extremely low background concentration of each of the target metals. Next. Now, the research has taken over 3 years, so I won't be able to go into all the individual improvements we made during the course of the project, but I will be able to show you a comparison here between where we started and where we are now. So there are only 4 key metals that are at measurable levels in our sorbent material, and those are chromium, manganese, nickel, and copper. Through a series of improvements to the material production process and steps to prevent contamination, we've significantly reduced the background metals to levels that are insignificant for most applications. To tie this in directly with gaseous fuels applications, let's use the example of the SoCal Gas Rule 45 trigger limit for copper, which last I checked was 0.06 milligrams per cubic meter, or 60 nanograms per liter. A typical sample gas volume for a sorbent tube is 30 liters, which means sampling gas from an RNG producer with gas containing copper right at the limit would result in a total of 1,800 nanograms of copper in the sorbent tube. The background copper in our tubes has been reduced from 445 nanograms to 9 nanograms, 9 nanograms, which as a percentage of the expected capture at the limit is a reduction from 25% to 0.5%. Next. So the sorbent material is now clean enough to use, but what about the plugs that separate the sorbent sections? Those are included in the analysis as well. So the background has to be very low in those plugs. 3 plug materials were tested over the course of the project. The first plug material was a common material we use in several other measurement applications, and it turned out to have unacceptably high concentrations of several metals, as you can see here. The second plug material was a significant improvement over the first, but it contained high concentrations of lead, and it created flow issues in the tube due to its high density. The third material had relatively low metals across the board and did not create any issues with flow. This material, which is a special type of foam, is now the standard for all tubes. Next. The last component of the tube to consider is the tube itself. The original tubes we used for this project included a ceramic label on the exterior with our logo and a barcode with the sample ID. And we noticed when we were using that type of tube that we had intermittent high concentrations of cadmium and lead, but the problem only occurred when analyzing an actual tube and not just the blank material inside the tube. We saw that the high concentrations were there even if we processed a brand new trap or a brand new piece of glass for the tube straight out of a box. So we assumed that it had to be either the glass itself, which didn't make sense, or the ceramic labels on the exterior of the glass. We asked for the material specs from our glass producer and discovered that we were right. Both cadmium and lead were present in the dyes that they use to produce those ceramic labels. So we switched over to glass with etched sample IDs, and we saw the cadmium and lead background drop to undetectable concentrations. What we think was happening here is as we were processing these tubes, part of the process is we have to use nitric acid in the lab to rinse out the interior of the tube, and occasionally a drop of that nitric acid would get on the outside of the tube, run across the surface of the ceramic label, and drip down into our sample digestion vessels. And that one drop of acid could contain huge concentrations of cadmium and lead because it was stripping it out of the label, and it was interfering with our measurements. Next. After ensuring the sorbent tube and all its components had sufficiently low background metals, the next step was to measure the capture efficiency. Capture efficiency is determined by the breakthrough percentage, which is the mass of metal collected on section 2 divided by the mass collected on section 1. Next. The first step towards determining capture efficiency was to test it in the lab. We did this by generating metal hydrides, which are essentially unstable gaseous metals that can form in anaerobic reducing environments like a landfill or a digester. Metal hydrides were produced by adding a sodium hydroxide, sodium borohydride solution to a reaction vessel containing hydrochloric acid and a metals standard. Not all metals can form hydrides, but using this combination of reagents, we were able to produce gas phase arsenic, antimony, mercury, and selenium. Next. And these are the results from that experiment. Overall, we had very good results. The average breakthrough for arsenic was 18.7%. You can look at that bottom row right there to see a summary of the breakthrough percentage for each metal. So arsenic was 18.7%, antimony 0.6, mercury 10.9, and selenium was 0. The conditions of the experiment were actually fairly harsh, since the mass loading for each metal was far greater than what we would expect to capture under any real sampling scenario when sampling biogas. And it was all deposited on the trap, or sorry, on the tube sorbent over just a few seconds, since the formation of metal hydrides happens almost immediately after the sodium borohydride is added. Next. So now I'm going to show you some field data. We took tubes that had that original design, and we took them out into the field and collected samples at a raw landfill gas site. And to our surprise, the tubes performed much worse with real sample gas, and our breakthrough percentages were very high. You can see that in the 3 sets of breakthrough percentages on the right side of the table here. They're ranging from 19.6% up to, in the case of lead on the bottom right, 430%. You can probably ignore the copper here, since all of those measurements were close to the blank level, so essentially we didn't really capture any copper, but the arsenic, antimony, and lead breakthrough percentages were all unacceptably significant. So we considered what could cause the tubes to perform worse in the field than they did in the lab, and we determined that it may have to do with the form of the metals. So our lab experiment that I just showed you with the sodium borohydride only included metal hydrides, and it did not include methylated metals, which are actually present at very significant concentrations in biogas relative to metal hydrides, according to literature. It also did not include any compounds that may interfere with the sorbent material's ability to hold on to those very volatile metals. So we went back to the drawing board and tried to determine how we could enhance the capture efficiency of the sorbent, and we came up with 2 different approaches. Next. So we treated a batch of sorbent material using what I'll call treatment method 1. And then we assembled a few sorbent tubes and went back into the field to the same site to collect a few more samples. And as you can see, 3 out of 4 of the samples exhibited significantly better breakthrough percentages. Once again, copper can be ignored here, since the measured concentrations were at the blank level. And likewise, we didn't see any significant lead this time. So we really only saw arsenic and antimony, and between those 4 runs, 3 of them had very good breakthrough, from 0.1% to 0.4%, but 1 of the tubes showed significant breakthrough. That's the 3rd one here. So we tried to determine what could cause that. Why would 1 of the 4 tubes exhibit high breakthrough? And we determined that it was likely due to an uneven application of the treatment method to the material. So essentially, this treatment procedure requires a very careful deposition on the surface of the sorbent, and our procedure almost certainly did not yield a homogeneous product. So we think that part of the product essentially had a lower concentration of that treatment and did not perform as well. So we went back to the lab and proceeded with the 2nd treatment procedure. Next. After treating the material with the 2nd treatment procedure, we returned to the field and collected 8 samples. So this table obviously is a lot noisier than the previous ones. I'm going to go through this a little slower. I'll direct your attention towards the left side of the screen where the sample IDs are. You'll notice that in addition to the S1 and S2 samples, which are section 1 and section 2 of the tubes, we also have samples that end with an F. Those are samples that had a filter included in front of section 1. And then you'll also notice, if you look in the notes column on the right, we sampled at different flow rates. So there were actually 3 different things that we tested simultaneously during this experiment. One was the effectiveness of that 2nd treatment procedure. The second was whether we would find any measurable filterable metals in the gas. And the third was whether the flow rate has any impact on measured concentration. We hoped that the flow rate would not have an impact on the measured concentration, and we found that it, in fact, did not. Although if you look at the data, these are all consecutive measurements, and these are in order chronologically. The concentrations do seem to go down over time for both arsenic and antimony, but the flow rate goes up and then back down. So there was no correlation between those two things. And we also found that there wasn't a significant amount of filterable metals. So with those two parts of the experiment aside, I want to focus on the key point, which is, again, capture efficiency as measured by breakthrough. We see that in this case, with all 8 of the sorbent tubes, our breakthrough percentages were extremely low. Our average breakthrough was 2% for arsenic and 0.2% for antimony. So we determined that treatment procedure 2 was significantly more uniform. We were able to produce a homogeneous product and decided to move forward using that procedure to make all tubes for gaseous fuels. Next. So with the background reduced to sufficiently low concentrations and the capture efficiency optimized, the next step was to compare with method 29 to ensure the two methods agree. Next. The first comparison test between method 29 and the sorbent tubes was designed to provide a significant number of replicate measurements. So I have sort of a scheme here, a diagram that explains how this experiment was set up. The samples were collected in quadruplicate. So we had 1 pair of method 29 samples against 1 pair of sorbent tubes per run, and we did that 6 times, giving us a total of 24 samples. Doing the test this way allows for the calculation of what's called relative deviation. So that's the absolute value of the difference between 2 concentrations divided by the sum of the 2 concentrations. It allows for the calculation of relative deviation between the tubes, between the paired method 29 samples, and between the 2 methods. Normally, the impingers in a method 29 sampling train are all combined into a single sample for analysis. So remember, I showed you that diagram. There were 3 impingers. Normally, all 3 of those are combined into 1 sample solution. When you do that, you are not able to determine whether any of the metals broke through the first impinger and got into the second impinger. We changed that procedure. We retained the first impinger solution in its own sample container and then took the second impinger solution combined with the empty third impinger, which was just rinsed with nitric acid and peroxide, and set that aside as a separate solution. Doing it this way would allow us to determine whether any of the metals in the gas made it through impinger 1 and into impinger 2. Next. So these are the results from that experiment. Again, I apologize for the very busy slide here, but I'll walk you through it. On the left side in green, we have sorbent tube data. The method 29 data is in blue in the middle, and the relative percent difference, which actually, sorry, I mentioned the relative deviation before. Relative percent difference is a little bit different. So note that we have relative deviation and relative percent difference on this table. Relative percent difference is the absolute value of the difference between 2 measurements divided by the average. So each of the methods, method 29 and the tubes, has 3 columns. We have concentrations, breakthrough, and relative deviation. And as you can see, the relative deviation for both methods was excellent, showing that the measurements were repeatable within each method. And you can see if you look at the bottom row there, under average for relative deviation for the sorbent tubes, arsenic, we had 4.1%, antimony, 4.1%. Then go over to the right, method 29, relative deviation, 3.9%, 2.6%. This shows us that we had very good repeatability, which is what we hoped for. The methods should at least agree with themselves. And they did. We also calculated the bias between the methods, and that's the relative percent difference on the right. And you can see that we actually did have a difference between the methods. Method 29 was always lower than the sorbent tubes. The relative percent difference for arsenic and antimony are at the bottom there. So 25.4% for arsenic and 16.1% for antimony. It's not terrible. The agreement could be a lot worse, but it could be better. So we tried to determine what could cause this bias. We almost immediately hypothesized that the low bias in the method 29 samples was due to arsenic and antimony breaking through the second impinger and ultimately escaping to atmosphere. So I want to direct your attention to the breakthrough, which is the middle column of each of those two sections, the green and blue. If you look at the sorbent tubes, you have 2.5% for arsenic and antimony, but the method 29 showed a very high breakthrough percentage, 62.3% for arsenic, 53.6% for antimony. What does that mean? Again, that means that in the case of the tubes, the metals are getting caught in the first section and they are not making it through. They're staying there. But for method 29, the metals are going into the solution in impinger 1. They're reacting there, but not completely. Some of the metals make it all the way through into impinger 2. So we hypothesized that if that reaction rate, essentially, how reactive the solution is with the metals, if that reaction rate in impinger 1 is the same as impinger 2, and it should be because they are both exactly the same concentration of nitric acid and hydrogen peroxide, we could calculate how much arsenic and antimony would be lost through impinger 2 through the meter box into the atmosphere. The way we determine that basically is by assuming the ratio of impinger 2 mass to impinger 1 mass is equal to the ratio of the mass lost to atmosphere to impinger 2. You can use that to calculate the mass lost to atmosphere, and then if you take that mass and add it back into the total, you can come up with a new total and compare that with the sorbent tube measurements and come up with a relative percent difference, which is what we did at the bottom of this table. So when you add that loss to atmosphere mass, which as you can see is the 76.6 nanograms, in this case I calculated it as a concentration, nanograms per liter and 81.6 nanograms per liter. If you add that back in, you get a relative percent difference of 2.1% for arsenic and 5.4% for antimony. Obviously, this looks great. This looks like very good agreement. However, that is a mathematical correction based on a hypothesis. It's not hard data. So what we are working on right now is returning to that same site and making changes to the method 29 sampling procedure, essentially sampling with 6 impingers in series, in order to characterize the breakthrough through several impingers to determine whether the concentration gets lower and lower through each impinger, and if we add up the mass that was collected in the full sample train, whether that mass would equal the sorbent tube mass. We expect that it will. I don't have results from that experiment yet. We have completed the experiment. The samples are in our queue right now. Unfortunately, we weren't able to get them done before this webinar, but I would be happy to follow up with anyone who is interested in seeing those results. Next. Okay, so we have some good data so far, but where does the method actually stand right now? The sorbent tubes are available for use right now, although we recognize that some facilities may require a published ASTM standard before they will accept it. That being said, an ASTM standard does not currently exist for method 29 either. We only have a modified version of a method that was created for emissions. The draft standard for using sorbent tubes to measure metals and gaseous fuels has been submitted to ballot at the ASTM DO3 Committee on Gaseous Fuels. It's gone through one round of voting. I've gotten a lot of good feedback. I'm making a few small changes to the standard. I have a few more comments to address. If anyone's interested and is a member, this standard is called WK91049. It will have a normal standard designation once it finishes the balloting process. I am hoping to have this published within a year. I actually think that's a pretty long time, so it can most likely be done well before that, but it depends on the voting process. The way this standard was written, it's as comprehensive as possible. So it describes the sampling procedure as well as all of the analytical quality controls, which are all based on EPA method 6020B for analysis of metals using ICP-MS. Excuse me. It also includes performance criteria for the development of an alternative sorbent material if somebody wants to use this method, but they don't want to use sorbent material that is produced by Ohio Lumex. Next. And with that, we've reached the end of my presentation. So thank you all for your time, and I look forward to your questions.
Awesome, Jonathan. I didn't know that anyone could have the superpower of being able to explain sorbent tubes and measuring metals and gaseous fuels so well, but you certainly have that, and well done. That was really great. For any of you that have questions, go ahead and tap them in or type them into the questions part of your control panel there. And just to start us off here, Jonathan, what has been the reaction of EPA to this, especially since they're the ones that have managed the common practice of method 29? Have they interacted with this much at all, and are they supportive or not, or where does that stand?
Yeah, they're very supportive. I'm going to see if I can turn on my camera here. They're very supportive of the method overall. Obviously, they're funding the emissions side of this. Initially, I didn't think they would be very interested in the gaseous fuels applications because that wasn't the purpose of the research initially. But it turns out they are very interested in it. They're very, I'll even say, thrilled by the data that we've gotten so far because the performance has been extremely good. By performance, I mean, the agreement between the tubes, the breakthrough, repeatability, et cetera. It's been very good. So yes, they've been extremely supportive. Obviously, their primary focus is on characterizing pollution. They're mostly interested in those air applications, but yeah, they're keeping an eye on this as well.
What about timing? Someone's got a sample, and I guess let's combine two of these questions here: the timing and the staffing required to take the samples. Can biogas producers, can they take the samples themselves? Do they need to have someone do it? And what kind of timing does it take to get the testing done?
Right. Okay. So two parts to that. The first part is actually a huge advantage with the sorbent tube method because the sorbent tube can be collected by one of our customers in the field at their facility with very little training or no training. It could simply be an email with a bullet point list or a one-page SOP and some very simple equipment. That is not true for method 29. Method 29 is complicated. You have to mix chemical reagents in the field without contaminating them. There's, obviously an exposure risk there, and the actual method of pulling gas through the impingers is not as easy as it is for the sorbent tubes. The second part of that, how long does it take to do this? So the actual sample collection part of it is 1 hour. The turnaround time for analysis right now, so after you collect that tube, you put it back in its container, you ship it to our laboratory, we'll begin sample preparation and analysis. That's the longest part of the whole process. Right now, that is a 2-week turnaround time. We are expecting to get that down to 7 business days. It's just a matter of scaling things up at this point. Yeah, hopefully that addressed your questions.
Yeah, thanks. It did. And let's see, I think this is our last question here. So have utilities accepted this method for demonstration with tariff requirements?
So this is a hot off the press, brand new standard. The data that I'm showing you is very fresh. We have talked to several utilities, and what they would like to see is essentially some kind of paper that would include a lot of the data that I just presented to you, as well as as some other information that's going to come out in the near future, like that experiment I was just explaining where we showed true agreement between the two standards. It's really up to the utility whether, what that threshold of data is. We know that some utilities are going to wait until there's a published standard, and others don't need to wait for that standard to exist. They're satisfied by seeing the data, proving that it works.
I might have said the magic word here because we've got other questions going in here now. But what would be the sample hold time? In other words, the time between sampling and analysis.
Right, that's a good question. Technically, that is something that has to be determined experimentally, where we collect samples, we put them on a shelf, we collect them all at one point in time. We put them on a shelf, we analyze some after a day, some after a week, some after a month, some after 6 months. That's a sort of like ruggedness study to determine how long the tubes can be held before they're no longer good. We have not done that experiment, so I can't tell you how long they would last, but I can tell you just based on chemistry principles, knowing what's happening with these volatile metals reacting with the specially treated sorbent material, that I would expect it to be on the order of years, not days or weeks. So hold time should not be something that you are concerned about. It is certainly longer than the method 29 hold time, which granted is still fairly long because the metals are kept in an acidic solution.
And you talked about expanding the testing to other metals and the interest, at least in California and some other places, of adding some other adding tests for other metals to this. What does that look like from your perspective right now? It sounds like your procedures here can be expanded to other metals, but is that something that you've tested already and you know can be done? Is that something that will take some time to develop? How will this testing be expanded for other metals as it's required?
Right, that's a good question.
Other entities. Yeah.
Right, so right now, arsenic, antimony, copper, and lead are all analyzed by default for all gaseous fuels applications. For any emissions application, there are about 14 metals that we analyze every time, and there is some overlap with the gaseous fuels applications. The thing is, when we do the analysis, the raw measurement doesn't discriminate between whether it's an emissions trap or an emissions tube or a gaseous fuels tube. We have calibration standards that include all of these metals, and we're analyzing the tubes and measuring all of those metals. We're only reporting those four for gaseous fuels because that's what has been requested. But in reality, we already have data for a lot of other metals, and we know for sure like chromium and cadmium are not going to be an issue at all. It's just a matter of going back, looking at that raw data and putting it through the report generation process to determine how the tubes performed for those other metals, to determine if we could expand to say, nickel or selenium or barium. My expectation is that it's going to work for all of those other metals as well, because the primary difference between gaseous fuels and emissions is the form of the metals. Again, gaseous fuels metals are volatile, right? They're hydrides, they're methylated, but not all metals can form hydrides. So if those other metals are present in the gas stream, they're likely to be either elemental or oxidized, which is exactly the same as what you find in an emissions trap. And we know that the emissions traps are tubes. We know those emissions tubes are working well for those other metals, so there is no reason why the gaseous fuels version would not work for those metals as well.
Excellent. Well, thank you. That's all our questions that we have right now, and we really thank you for sharing this with everyone and for your support of the American Biogas Council. I hope all of you will go check out Ohio Lumex for your gas analysis needs. And with that, we are going to close today's webinar, and just be aware that there'll be a survey that pops up right as you close this. Please take a minute, and I promise you it'll only take a minute or two to respond to that. And thank you all in the audience for your attention. Have a great rest of your day.
Thank you.